This video is about electrochemical or voltaic cells, and by the end of the video you should be able to identify an anode and a cathode in a cell, explain the use of a salt bridge, explain how a battery works in terms of electron and ion transfer, and calculate the cell or battery's voltage or electromotive force. In order to do that, you should already know how to do oxidation numbers and identify redox reactions. So the question of this video is, what is the voltage of a standard AA Duracell battery or technically any battery that looks like this that you might have at home? So in order to answer that, let's talk about voltaic cells. In a spontaneous or favorable oxidation reduction reaction or redox reaction, electrons are transferred and energy is released. In this example, what you're seeing is that there is zinc atoms in the strip and a copper solution in the blue liquid. And what's happening over time is the zinc atoms in the strip are losing their electrons and it's dissolving the zinc. So what used to be as a solid is now in an ion form away from the solid. The copper atoms are formed because there is copper blue solution and the atom obtains the electrons to form, the ion obtains to form the electrons to form the atom. And so on the outside and macroscopic scale, you're seeing all these what looks like black, but it's actually like penny colored particles on the outside and falling to the bottom because they're precipitating out of the solution. You'll also notice the solution went from dark blue to lighter blue because we have less ions over time. We went from a lot of copper ions to less copper ions. So in order to figure out how much electrons are transferred, we can actually separate those particles into two separate beakers. So now you have a copper metal in a copper solution and a silver metal in a silver solution, and we're forcing electrons to go through an external device. They're going through this voltmeter, through the wires, and then into the other side. And that setup is called a voltaic cell. So this is what it looks like in real life. And then we have some pictures that depict that pretty often. So what this is the same example that we just saw, but in a drawn form. So oxidation occurs at the anode, which is negative. This is the zinc anode. It is made out of silver atoms that are currently forming ions. The zinc atom forming ion is an oxidation where it loses its electrons, right? Oxidation means the charge goes up, and Leo says lose electrons. The electrons go up through a switch through the voltmeter, which registers how many electrons are going through that voltmeter to tell you the voltage of the cell. And then they deposit themselves on the copper cathode. That's the copper colored, penny colored solid. That copper cathode attracts copper ions that are in the solution, which is giving the solution that blue color. You can see the copper ions are going up to the cathode, and they're gaining electrons that were coming through the voltmeter. And that forms copper solid, on the outside of this cathode. You'll also see a salt bridge, which we're going to get to in a minute. And what we need to start to memorize is that the anode is always where oxidation occurs, and the cathode is always where reduction occurs. They're just the names of the parts. Some people remember red cat and anode ox. The vowels go together, so anode oxidation and the cathode reduction are the consonants that go together. So electrons always will be moving from the anode to the cathode. I like to remember it as alphabetical order, but that's because the anode's losing its electrons. So once electrons flow from the anode to the cathode, the charges in each beaker would not be balanced and the flow of electrons would stop, right? Once one electron went here, you would have electron losing, and so this would become positive. And there would be no reason for electrons to go through the wire. If this is positive, they would be attracted. Therefore, we need a salt bridge to keep the charges balanced. What you'll notice is the anions go to the left side to push the electrons through, right? Negative hates negative. And the cations go to the cathode to keep that side positive. So cations to the cathode, anions to the anode. As the electrons reach the cathode, we said before that the cations in the solution are attracted to the now negative cathode, and they kind of force themselves on. So you're getting an increase in mass on the copper side. But we know that there's a law of conservation of mass. So if copper is increasing, this metal is increasing its mass, it's coming from the ions that were in the solution, not from nowhere. And in order for electrons to transfer, the zinc is actually dissolving. So it looks like this anode is decreasing mass. The anode is decreasing mass, but that's because it's going into the solution. So electrons are taken by the cation, and the neutral metal is deposited on the cathode. So the cathode, the actual metal, gains mass, and the anode, the actual metal, loses mass, but they're actually still in the solution. The electromotive force, EMF, is generated by those transfer of electrons. So a voltmeter may be placed in the wire to see how the transfer of electrons are going. We call it electromotive force, or E for short, right? So the cell potential, or E of the cell, these are all synonymous. So the cell potential is measured in volts, and you might have heard like voltages before, but you might have also heard watts. So there actually is a difference between watts and volts. Watts is a method of measuring the rate of energy transfer, or rate, how fast it's going, and the power of that rate is going in wattage, or watts, and they're the products of voltage and current, so the electrons moving through the substance. So the wattage tells you if you have a bright light or a light like dim light, whereas a voltage is a force that makes electricity move. And so the difference between the two types of anode and cathodes that you have, if you switch a light on and off, the voltage is still going, is a potential for the electrons to go through the container. There's also an amperage, which is the unit of current equal to the flow of a coulomb per second. So this is kind of confusing, and it's really important in physics class. So I really like the analogy down here, thinking about like a hose that's spraying water, outside, maybe for example, or filling up a pool. You're using that hose with a spray nozzle. And so if you're thinking about that hose, in that analogy, the voltage is the pressure of the garden hose. So even if the nozzle is turned off, there's like a pressure build inside your hose, right? That's trying to push the water out. That's going to be your voltage, the ability for the electrons to go through the circuit. The wattage in this analogy is, imagine you're spraying that water from the hose into a bucket. The wattage is how quickly the water is going up. Remember again, wattage is the rate at which it's going out. So which is why we're saying the more wattage that you have maybe in a light bulb, the brighter the light, because it's going out at a large rate. And then an amperage in the hose analogy is when the water is turned off, there's still water in the hose, but there's no flow, right? So it's getting stuck. The amp of the current is the flow of that, so it's zero flow. And then once you turn it on, you can measure that flow. So in terms of electricity, a light may be turned off, but the currents are still sitting in the wire, they're ready to flow. We're really recommending, really looking at voltage in this topic the most. So the values are represented by the standard hydrogen electrode. We decided that the hydrogen electrode is going to be a 0 value, and then whatever you put, if you put hydrogen on one side, whatever you put on the other side, this metal, is whatever the voltmeter reads as a number of electrons that are going through, that's going to be assigned to this metal. So that way you say the difference between hydrogen 0 and this metal is the metal's value. So by definition, the reduction value of hydrogen is 0, and then because we need everything else to compare it to, and that's specifically at 1 atmosphere and 1 molar solution. So if you change those parameters, it won't be 0 volts anymore. And then from there, we can get a bunch of other reduction half reactions. So since we're only going to use a certain amount of them in labs, I gave you a certain list. This is a list that we're going to be using. There are tons more, but this is a short list of reduction potentials, and they're measured against the hydrogen cell, right? So when you see a hydrogen cell reduction is 0, and then these ones are all better at reducing than hydrogen, and the ones on the bottom are all worse at reducing. Therefore, probably better at oxidizing than hydrogen would be. They could flip. They didn't give you a reduction and an oxidation half reactions because oxidation would just be read backwards, and then therefore you would negate the cell. In order to find out a full cell, what you're going to do is read the reduction at the cathode value, and then you look for the anode and reverse it. So that's why you can see it as cathode minus anode, because it's reversing the anode for you. So we don't multiply any voltage, unlike enthalpies, and this is because the voltage is depending on the radius of the atoms, not the amounts of the atoms. So it's actually an intensive property, meaning that it depends on which atom you have, not how many you have. So the length of time the battery is working is dependent on the number of atoms, but that's different. That's not the voltage, right? We're talking about wattage and amperage then. So we're just looking at voltage, or the ability for electrons to transfer. So if we were to do it for this cell that we've been seeing for zinc and copper, we can look up the reduction tables, and right now what's reducing is copper. So copper I just read normal, 0.34 volts, and the zinc is oxidizing, so I had to read zinc backwards. Its oxidation of the cell is the reduction is negative 0.76. So I have to reverse that. You can either think of it as now make it positive and sum them and you'll get 1.1 volts, or if you do cathode minus anode, it's negating that anode for you and you'll get 1.1 volts. So you remember, you have to think of it one of two ways. Either that you're going to reverse the oxidation and sum them, or if you want to do cathode minus anode, it reverses the anode for you. You're not doing a double reverse, right? Just one negation. Sometimes they show the cell in like this weird notation where what it's saying is there's a zinc and there's a phase membrane to zinc ion. So this is a solid, this is the ion, and they're in their same container. And then there's a salt bridge, that's the double line. And there's a hydrogen solution, maybe acid, with hydrogen bubbles. And in this case, if we wanted to find the voltage, we would say, well, let's look up to some of the values. If you look up hydrogen, its reduction voltage is 0. We probably knew that. And then the zinc is better at oxidizing, so we're going to reverse the zinc. And so you can see cathode minus anode, I reverse the zinc. And we say that if these two got together, they would make a 0.76 voltage. If you want to try it again, here's an example with hydrogen and copper. Again, hydrogen is 0 if it's at the cathode, and copper is better at reducing this time. So what we're going to do is we're going to make copper reduce, and it's at 0.34, and then subtract the hydrogens, which didn't matter because it's 0. So this would be a 0.3 voltage cell. If we put the zinc with the copper as we previously did, what we're saying is zinc is better at oxidizing, and so we're reversing that 0.76 that we looked up to be positive, and the copper we leave alone because it's reducing 0.34. And so that's a total of 1.1 volts. Another type of question you might see is, can tin reduce zinc spontaneously? So what you would have to look up is the reduction potentials. Tin is better at reducing at a higher voltage, so zinc would oxidize spontaneously, not reduce. So it's saying tin reducing zinc. Will zinc reduce? No, it's better at oxidizing. And then calculate the electromotive force, which really just means voltage, of a cell with magnesium and a magnesium ion and silver and a silver ion. So again, these are just all similar questions. You're going to look up your potentials and see that whichever one is better at reducing, you write first, and whichever one is better at oxidizing, silver, you have to negate. So it's no longer negative 2.37, it's positive 2.37, for a total of 3.17 volts. Out of the things we just talked about, this would make the most, the highest voltage, so the strongest battery, out of the 4 that we've seen. So back to the question of the video to sum it up. What's the voltage of a standard AA battery? So with a AA battery, if you look it up, the anode is zinc reacting with hydroxide ions in the salt bridge. So this is the reduction, the oxidation, sorry, because zinc's going from 0 to +2. The oxidation number of 1.28. They negated it for you already because it says ox. And then manganese dioxide is at the cathode. And so here's manganese dioxide going from a +4 to a +3 ion. So it's going down in charge and gaining electrons. And a reduction potential is 0.15. When you sum these, the 2 electrons transferred perfectly, 2 to 2. You can cancel them out. Also, the waters will cancel out and the hydroxides will cancel out. So the reaction that's going on in the battery is zinc is reacting with manganese dioxide, but one side is zinc and one side is manganese dioxide. So you need the battery to be plugged into a wire in order for this to work. And when it does, we're calculating a 1.43 voltage. They report it, if you look really closely, as 1.5 volts. At this point, you should be able to identify an anode and a cathode and explain the use of a salt bridge, talk about electron and ion transfer, and calculate the voltage of a battery.